Where's my first sheet? Yeah.
All right. Thank you.
Okay. Can everyone hear me? So firstly, I want to say I'm absolutely delighted to see so many young people here interested in Iwasawa theory. That's fantastic. And for that reason, I want to actually, of course, the strict formal notes of my lecture are up on the website, but I thought I should, perhaps it's the privilege of an old man, to say a few words, well, the first half of this lecture, because my first lecture is very basic material that I'll say a little bit about in the remaining minutes. But I thought, first I should say something about Iwasawa theory in general, partly historical, just to try and somehow give a glimpse of the whole picture of the subject. So let me begin straight away, and I hope people can read. I'm not very used to this machinery, but let me just remind you, so F, with the base field, will always be a finite extension of Q, and I'm going to write F infinity for what we call a ZP extension of F. In other words, that's a Galois extension of F, whose Galois group is isomorphic to the additive group of p-adic integers, and this is for any prime p. The prime p is completely up to us, and in particular, the subgroup, the only closed subgroups, of course, of ZP are p to the n ZP, and so there'll be the corresponding closed subgroups of the Galois group, and if you take, it's usually called gamma n, I'm going to do that now, for the subgroup of index p to the n, and of course, the part of F infinity fixed by gamma n will be a cyclic extension, Fn over F, of degree p to the n, and we often call it the nth layer. So out of my ZP extension, I've got this tower of fields, F0, F1, and so on up to Fn, up to F infinity, where Fn for every n is a cyclic extension of degree p to the n. So that's an equivalent definition of a ZP extension. This is the type of object that we will all be talking about in the lectures. Now I want to talk about, in this sort of general introduction, what I will talk about four facets, four different sides of Iwasawa theory, very generally. I'm not going to get down to brass tacks. That will be done in the lectures. And of course, the first facet will be the, in some sense, traditional Iwasawa theory, and it has several sides to it. The first one is what I'll call classical Iwasawa theory. So we have now our ZP extension, F infinity over F, and classical Iwasawa theory is concerned with the p-adic behavior of the ideal class groups and the unit groups in this extension, this ZP extension, F infinity over F, and the interpretation of these objects via classical global class field theory. And this is what I will call classical Iwasawa theory, and it was what got Iwasawa going on the whole subject. Now, the test begins. So, but there's another side of this classical Iwasawa theory that was discovered by Iwasawa. So let me remind you that I better put 2 on this to remind myself, that the Riemann zeta function, zeta of S, is given by the product, it's complex zeta function that you all know, given by this Euler product when the real part of S is bigger than 1, and of course it has an analytic continuation and so on. Now what we should remember is that there's of course an immense amount of work going on complex L functions in number theory, but ultimately their interest for number theorists is not to do with the analytic continuation and all. This is just a step along the way. The ultimate interest is with arithmetic questions. Well, let's not forget that. And the most classical, well, it's not the most classical, but the one thing I want to mention first is the behavior of the complex zeros non-trivial zeros of zeta of S are related to the distribution of prime numbers. This, of course, is Riemann's great discovery. And in some sense, there is a similar question for all other complex L functions. But this is the one side of complex L functions that is deeply concerned with arithmetic questions. But up till now, we have never discovered a p-adic analog of it. Iwasawa theory is a p-adic theory always. So that this is the one side which is not. But there's a second side which I want to mention now, which is, and it's tied up with the fact that the values of the Riemann zeta function at the odd negative integers are rational. This is for n equals 2, 4, 6, and so on. These are rational numbers. And Kummer was the first person to realize that they were deeply concerned with the class number of the field, the p part of the class number of the field, Q adjoin the p roots of unity and then take its real subfield. Kummer discovered this about the same time as Riemann. But it was not, well, the next important step along the way was due to Leopoldt and Kubota, who proved the existence of a p-adic analog of zeta of S. Now, I'm not going to spell it out what this p-adic analog is. It's actually, if you like, there are p minus 1 over 2 branches, or it's a measure on a Galois group, but there's a very precise p-adic analog. But they had no idea of, as far as we know, of its connection with deeper questions, and that is what we owe to Iwasawa. Iwasawa made the, now maybe I can put that there. In his beautiful paper, which no one reads, called On Some Modules in the Theory of Cyclotomic Fields, which was published in the Mathematical Society of Japan in 1966, I think, something like that. But he made the extraordinary discovery that you have to combine it with a paper, little paper he published later in the Annals, that the zeros of this p-adic analog of Leopoldt Kubota were precisely and deeply connected with the behavior of the ideal class group and the units, if you like, the p-adically in the tower Q. So Iwasawa, maybe I should write something here. Made the discovery that the zeros of the p-adic analog of zeta of S are related to the arithmetic, the p-adic arithmetic. Well, let's put it like this. The classical Iwasawa theory that I was talking about before of the tower Q adjoin all p power roots of unity. Well, you can say it several ways, but let me take the real subfield over Q of mu p plus. And this great discovery of Iwasawa's, which is purely about the Riemann zeta function, became known as the main conjecture. Now you should be a little bit careful with this terminology, that originally it was a conjecture, it was then proven. In fact, Iwasawa himself proved a very beautiful first step which went a long way towards proving the theorem, the main conjecture. In fact, it proved it when the class number of Q of mu p plus was prime to p. But it was only later that, but he formulated it. It was his discovery that Maser and Wiles gave the first complete proof. And this main conjecture is, I'll be talking in a moment about its generalization, is perhaps the most mysterious side of Iwasawa theory and the most useful for studying arithmetic. Now, I should say that there is one very interesting problem about the classical complex Riemann zeta function, p-adic analog of that, which is unsolved, and which it would be very interesting to solve, namely that it's a fact that zeta of S has a simple zero. This follows simply from the functional equation at S equals minus n for n equals 2, 4, 6, and so on. This is the same, of course, as saying that something that this is because we know that zeta of 1 minus n is an odd positive integer, and it obviously doesn't vanish. But the p-adic analog of this statement must be true, and it has never been proven. It's a very simple question about, which in fact I believe has significant applications to homotopy theory and things like this, that we do not know how to prove the simple analog of this statement, which I'm not going to say precisely because it involves a little bit with branches of the Leopoldt-Kubota function. Okay, so that is all I want to say about facet 1. And, sorry, the first facet. No, it isn't. Sorry, now there's yet another aspect that I want to mention, namely that what is the use of Iwasawa's main conjecture for Z? Well, there is one important application, namely that Quillen defined the higher K groups of Z, the K2nZ, for n equals, in fact, for every positive, every non-negative integer n, you have these mysterious groups which come out of homotopy theory, and there was a lot of interest of them. This is how many of us got started on Iwasawa theory, that in the early 1970s, let me keep to my notes here so I don't get too lost, that Borel and Garland proved that the K2nZ, this is for n equals 1, 2, and so on, that these are finite groups. This is a highly non-trivial result. Whose proof depends on differential arguments in differential analysis, differential topology, and so on. And what was really interesting, this is certainly how I became, I've got to work out what to do here. So that, No, I forgot. Well, anyway, what's going on here? Okay, so they're finite groups, and now what got us all started was that Birch and Tate first, and then Steve Lichtenbohm after that, came up with a remarkable conjecture that's now a theorem, namely that the theorem is that the order of these finite groups, K2nz, is the I think you have to be careful of a sign change perhaps in the zeta value, of WNQ zeta, the zeta function at 1 minus n, and this is for n, I'm sorry, I guess it's, it's 2, 4, 6, and so on. That there's a remarkable exact formula. This is a theorem now, and it was this conjecture which certainly got me interested in Iwasawa theory. I was fortunate to participate to a seminar that Tate was giving. I was a postdoc in Harvard at the time on this question, and my interest in Iwasawa theory arose from looking at this because it seemed to give hope of proving precisely this statement. And in fact, now it's a theorem. At that time, the main conjecture wasn't proven in general, but now it is, and this is actually a theorem. And notice it's telling us that the order of, it's got nothing to do with the prime p. It's a statement about the order of a finite group is this integer. The WNQ here, I should say, is a simple generalization of the number of roots of unity. Now you have to look at extensions where the Galois group is annihilated by n. How many roots of unity you can have in that. So that's a very beautiful application of Iwasawa's main conjecture straight away. And we, excuse me, we have no idea how to prove this theorem in any other way at present. My gosh, time is running on, so what I want to move on to now is facet 3. Facet 2, sorry. So instead of, up until what we were doing earlier, we were just looking at a ZP extension of a number field and using its properties to try and study arithmetic questions. But now let's suppose, again, we have our extension f over q, and I now have a motive, m over f. For example, the example that I'm going to talk about is I'm going to take f to be q itself and m to be an elliptic curve.
John,
Yes?
that formula is k2n minus 2.
Sorry?
K2n minus 2.
You're right. I'm sorry. It is k2n. k2 times n minus 2 times n minus 1. Yeah. I'm sorry. Yeah. That is absolutely right. Yeah. Anyway, the point is there's a formula, there's an exact formula for the order of the K group in terms of these zeta values, and we prove it using Iwasawa theory at every prime p. Now, of course, our elliptic curve has a complex L function, LE of S, which is entire. This is, of course, in the CM case, the theorem of Deuring, and in the non-CM case, the theorem of Wiles. that, now let me put that there. And then we have the celebrated conjecture of Bircham, Swinnerton and Dyer, which I'm not going to state precisely, BSD, but what it is, of course, is it tells us that there's a precise relation between the basic arithmetic objects here are the group of rational points on the curve and the Tate-Shafarevich group of the curve, Shah of E over Q, and the behavior of LES at S equals 1. And in particular, the remark I want to make is that it includes an exact formula for the order of Shah E of Q. And the point I want to make is that the only hope we have of getting at proving this exact formula is using Iwasawa's theory, and Iwasawa's theory for every prime p. And in particular, there's a very simple first step along the way, which I want to mention as a conjecture because it's not known in general, to give you some idea of of how Iwasawa theory comes in. Namely, the assertion is that LE of 1 is not naught if and only if EQ is finite and the Tate-Shafarevich group of E over Q, the P primary part, is finite, where P is a prime. P is a prime. And this should be true for every prime P. And in fact, what we know now, what is known? That the implication in this way is known. This is Collivagen-Grossagier. The implication in the other direction is known for most E and P sufficiently large. But I stress that you know, the whole Birch-Swinnerton and Dyer conjecture is a formula which works for every P. And in particular, there is this very interesting question. Now, maybe I can just write it here. Example, prove this for P equals 2 and the curve E y squared with complex multiplication x cubed minus n squared x, the congruence number curve. That has suddenly become, it is unknown. I mean, I hope it can be proven, but at the moment, no complete proof has been written down. But you see, let me stress that this is a very deep fact, if it's true, because what you're saying, you see, when you say that Shah EQP is finite, you're saying there are no infinitely divisible elements. And what Iwasawa theory is apparently saying is that if that is true for 1 prime p, then you see, then that will prove the L function doesn't vanish, and therefore by the Collivagen-Grossagier theorem, that will prove that there are no infinitely divisible elements for every prime p. So there is something really deep going on here, and it it's just an indication of how important Iwasawa's theory is, I think, with this type of question. Now, let me also, because time is running out, just say that what should also be possible in what we know at present with Iwasawa theory, but it's still quite a long way off, is if you have any elliptic curve over Q where we know that the complex L series has a zero of order at most 1, then the one thing that's lacking to prove Bert-Swinnerton and Dye is to prove the exact formula for the Tate-Shafarevich group, its order. But we should be able to prove that. It's again known for, in some sense, all but a finite number of primes for most curves, but this is perhaps in some sense an easier question in Iwasawa theory than some of the others I'm raising. But it should be possible to do this in the next 5 to 10 years. Okay, now I want to quickly mention two other facets of the subject. Oh, sorry. Just very briefly, so I don't know, maybe this is 6. So there is facet 3, that it seems that everything we can prove when p-adically, when f infinity over f is a ZP extension, should hold if instead we take an f infinity over f whose Galois group is a p-adic Lie group, any infinite p-adic Lie group, like GL2ZP, that there are some results in this direction, but again, in an ideal world, this should be true. And that's another important facet of the subject which should be clarified. And then finally, facet 4 I want to mention is this fact that it turns out, again, I'll only write down a few things, that it seems that some important modules which turn up naturally in Iwasawa theory are much smaller than you would expect from perhaps the naive algebraic theory. So for example, I mean, perhaps the simplest example of this is Iwasawa's so-called mu=0 conjecture for the cyclotomic ZP extension of any number field, which in that case, this is one of the few cases where things have been proven, of course, was proven by Ferrero and Greenberg, and Washington, and then Sinnott gave another proof shortly afterwards. There are other much more mysterious. For example, Ralph Greenberg has some very beautiful conjectures in this direction that I don't have time to talk about, where all the numerical evidence suggests that they are true, but we have no idea how to prove them. I think it's said. But I want to just end by mentioning one, perhaps the oldest example of this type of conjecture, which goes back in a very special case to Weber, and then was studied more recently by Japanese mathematicians, in particular Fukuda and Komatsu, and others. And the conjecture is the following. So let's let Q infinity over Q. It turns out Q, out of class field theory, has only one ZP extension, the subfield of the field of p power roots of unity. And so you can now look at the finite layers of this ZP extension, any prime p. And so let me now write Qn for the nth layer. So this is the unique sub-extension whose Galois group is P is any prime here, whose Galois group is cyclic of degree P to the n over Q in this extension. And now the conjecture is that for every n and every p, Qn has class number 1. This is totally surprising. The case P equals 2 goes back to Weber. Iwasawa proved long ago, it's one of the first results of his theory, that the class number of Qn is prime to P for every n. But this is a much stronger statement. It's saying the class number is always 1. And there's only, the Japanese mathematicians have found some striking evidence in support of this conjecture. And it would be very interesting to go further. And let me just remind you that even if we could prove it for P equals 2, we would have proven for the first time the existence of infinitely many number fields with class number 1. This has never been proven, even though, of course, there apparently, say for real quadratic fields, there are infinitely many with class number 1. Okay, so now I should perhaps discipline myself. I wanted to make these general remarks at the beginning so that you can see that there is important progress going on in practically every direction of what I've vaguely talked about here, and you'll hear some of it about it in some of the lectures. But it is important to keep in mind that Iwasawa theory has many arithmetic applications, potential ones like this. Okay, now in my remaining time I want to say a little bit about the notes. So in my lectures I will be talking about the very first subject, classical Iwasawa theory, and perhaps the first non-trivial and interesting theorem in that direction that is proven in this great 1973 Annals paper of Iwasawa's. And the first thing, of course, when one looks into Iwasawa theory is that you should say, well, we should talk about the Iwasawa algebra, lambda of gamma.
Could you just put sheet 5 that's under 6 on the, I think it's just Thank you.
Yeah, this is too much to keep track of. So let's just say a tiny bit about the algebraic theory. Now, I've talked about it rather in the notes for my lectures, which are online. I've summarized the results that we use over and over again, but let me just mention a few of the key ones. Now, firstly, so lambda of gamma is the Iwasawa algebra of gamma, which by definition it's the projective limit of the group rings ZP of gamma mod gamma n. And as Sarah remarked long ago, this is actually isomorphic, it's easy to see, to the formal power series ring ZP double brackets T, and in this isomorphism you see gamma, of course, an abstract Galois group isomorphic to ZP does not have a canonical generator. You can pick anyone. So in this situation, if you pick a generator, so gamma is a topological generator of gamma, then there's a unique isomorphism. In fact, here if you put the m-adic topology, this ZP double brackets T, of course, is a very special regular local ring of dimension 2. It has its m-adic topology, where m is the maximal ideal, and here there is a unique topological isomorphism in which you can send any gamma to 1 plus T. And then everything else goes by linearity and continuity and so on. Now, what we're interested in, and by the way, if perhaps I should mention the fact that we're going to be interested in modules that are finitely generated over lambda gamma. And of course, our modules will be always compact. There'll be X will be a profinite abelian p-adic. I mean, it's a ZP module, if you like. And the Nakayama's lemma will tell us that X is finitely generated over the Iwasawa algebra of lambda of gamma is equivalent to saying that the gamma co-invariance, so this is X, if you like, over gamma minus 1x, it's the largest quotient on which gamma x acts trivially, that this is finitely generated over ZP. Or if you like, that's the same as saying that when you divide it by the maximal ideal, you'd get a finite group. So this is the Nakayama's lemma in this case. And so what we're interested in is, of course, the category, I call it in the notes, R of gamma, of finitely generated lambda gamma modules. Because when you look at classical Iwasawa theory, this condition here is always seen to be true, essentially by class field theory, and so you have finitely generated lambda gamma modules that you're looking at. Now, it turns out that even though, of course, lambda gamma, or equivalently ZP double brackets T, is not a principal ideal domain, the maximal, it is of dimension 2, the maximal ideal is not a principal ideal, that there is a very beautiful structure theory of these modules, of modules over that, finitely generated modules over those rings, which is, in fact, you could take gamma, instead of isomorphic to ZP to the n, and it's beautifully explained, this structure theory, in chapter 7 of Bourbaki's commutative algebra. So that's where you can find all the proofs. And in fact, the main structure theorem is the following, because I want to state it now. Now wait, 5, 6, because Romeo, I know, needs it in his lecture. So the theorem is, and of course we need it too, that let's let M be a finitely generated lambda gamma module. Then, in fact, an exact sequence of lambda gamma modules. So we have M here, and then we have a homomorphism now to what we would have if lambda gamma was a principal ideal domain. So in other words, you'd have lambda gamma, some power of lambda gamma, plus a direct sum. Let me write it a second one from, say, I equals 1 to k Oh,
John,
whoop,
your head is fluffy.
how's that? Oh, head, over lambda gamma modulo Fi, principal ideals, from I equals 1 to k. So there is such a homomorphism, which is almost, which is what we call a pseudo-isomorphism. In other words, the kernel D1 and the co-kernel D2, D1 and D2 are finite lambda gamma modules. So this is this all-important structure theorem, and we use it over and over again. I'm going to mention a couple of uses in a moment, but let me say too that when you first encounter this, you think, well, my heavens, are these finite modules here superfluous? But you realize when you look at arithmetic questions, they are not. That they're really, when you look at, say, the arithmetic in these cyclotomic tower over a number field, that sometimes you really do need these. There is no escape. In other words, the algebra fits beautifully the mysterious arithmetic. So don't try and think that they're not there, but nevertheless they are fairly harmless. And in particular, you see, so that what are some of the consequences that you get straight away from this structure theorem? Let me mention one. So it's the lemma. You see, one would like to be able to determine, so this integer r is the lambda gamma rank of the module M. In the obvious sense, I mean, the lambda gamma rank of the finite module, you tensor this module with the fraction field of lambda of gamma and then look at the dimension over that space. Well, it's easy to see that for that element, this module there, that's indeed R. But what we want to do, how we use that in practice is the following, that in fact it implies that this is given one of the exercises in that people who are interested can do the exercise, that the ZP rank, and by that I mean the number of free copies of ZP of M gamma n. So now you take the gamma n co-invariance of this will be of the form p to the n times r plus delta for some delta fixed delta greater than or equal to naught. This is true when n is sufficiently large. So you see, the beauty of this statement is exactly how Iwasawa, we're going to give his proof, how he proved the weak p-adic Leopoldt conjecture as you go up the cyclotomic tower, because you see, this will enable you to determine the rank. If you can show that this n and gamma, you can determine, if you have a formula like this, you can say the r that you get there has to be the rank. So that's just one example of how important it is. And then similarly, I mean, again, my time is almost up and I want to say one or two things more, but I also explain how you make a characteristic ideal out of this. These Fi, which are non-zero here by themselves, are not uniquely determined, but the product of all of them is. And the ideal that the ideal it generates in the Iwasawa algebra is, and that's what we call the characteristic ideal of M. And that turns out to be very beautifully related to the Euler characteristic of M as a gamma module in these cases, when you have a torsion module. And the exact formula is again given in my notes. And that Euler characteristic formula is what you use to pass always from the Iwasawa main conjecture, which will be a statement over the ZP extension, to a statement, an arithmetic statement at the base. So that's, again, a very important fact that I think I don't have time to spell out here. Okay, now, for the algebraic theory, I think I have said most of the well, there's also the so-called mu invariant and so on, which you will see explained in my notes. But now what I want to end with, I must talk about this basic fact from class field theory, which underlies the whole of what we will talk about in the rest of my lectures. Namely, suppose that you have your number field F. So now this is, I don't know, but it doesn't matter. F over Q is finite. P is any prime. Then what we want to know is how big, suppose we look at the M over F, which is now M is not a motive, it's a number field, it's the maximal abelian P extension of F in which only the primes above P dividing P can ramify. So even the infinite primes, I do not allow them to ramify in that. And now, so what is this Galois group of M over F? Well, you see, this is where global class field theory gives us an answer which on the face of it is very beautiful. And the answer is the following, that we have an exact sequence. Well, firstly, it will map onto the so-called Hilbert class field of F. So this is the Galois group of M over F. And the P Hilbert class field, so this is, its Galois group here will be isomorphic to the P primary subgroup of the ideal class group of F. This is so-called Hilbert class field. Now what's the kernel here? Well, the kernel here is the Galois group of M over L. And class field theory, you have to look at the appropriate quotient of the ideal class group to see this, gives the following explicit description of this Galois group. Namely, you look at, firstly, I'm going to put UF to be the product over all the primes dividing P of the UV1s. I put the 1 in because I'm all the time looking at extensions in which are pro-P extensions, and so I want to take the primes congruent to 1 mod P to look at these are the local units here, and now I have the global units EF, which these are the global units which are congruent to 1 mod V for every V dividing P, and then I have the natural inclusion I of EF into UF. The global units congruent to 1 into there. Now let me put this here. I will finish in just 1 minute. And so then I can take the, what I'll call EF bar, which is the closure of EF in the p-adic topology. Of the image of EF in here. So in other words, it's, if you like, it's the ZP module generated by the image of F. And now, of course, by Dirichlet's theorem, EF has Z rank R1 plus R2, these are the real place number pairs of complex, minus 1 as a Z module. But now, once we take the ZP module that they generate, on the face of it, there could be p-adic relations between them. So all we can say is that in general, just in an elementary way, that in fact EF bar has ZP rank R1 plus R2 minus 1 plus delta, now I better stick to my notation in here, plus delta FP, where delta FP is some integer greater than or equal to 0. Sorry? Oh, sorry, minus, excuse me. Thank you, I'm glad some people are awake. And it's a celebrated conjecture which goes back to Leopoldt that delta FP is always 0. And now many people have tried to prove this, and there is still some truths floating around. I have no idea whether or not. Certainly, but I think in terms of having a published proof of this statement that the whole world can understand, it remains unproven at this point. And in any case, we're not going to be... So this is the so-called defect of Leopoldt. And the theorem that I want to discuss, I have to end now, but it's all explained in more detail in my lecture, is this beautiful result of Iwasawa, that if you take the cyclotomic ZP extension of any number field for any prime P, and you look at the defects of Leopoldt as you mount up the tower, that they are bounded always. This is Iwasawa's theorem, which is why we call the weak Leopoldt conjecture. And in the rest of my lectures, I'll be explaining how he proves that. For the cyclotomic ZP extension, of course, it should be true for every ZP extension, but we don't know how to prove it. Thank you.
Any questions?
So I'm wondering, when you were talking about the BSD conjecture, isn't the Tate-Shafer-Ravitch group supposed to always be finite?
Of course, but we can't prove it.
Can you repeat the question?
So in the Tate-Shafer-Ravitch conjecture, sorry, the BSD conjecture, it looked like you were saying, I was a little bit confused, you were saying that the L function doesn't vanish if and only if the Tate-Shafer-Ravitch group is finite?
And the group of rational points is finite. The conjecture should even be better. The Iwasawa theory should tell you that the L function doesn't vanish if and only if the group of rational points is finite, and for some prime P, the p-primary part of the Tate-Shafarevich group is finite. So in other words, that p-primary part has no infinitely divisible elements. So it's something much stronger than just finiteness of Shah.
Whereas I'm just trying to understand, isn't that supposed to be finite even if the L function vanishes?
Sure, but we have no idea how to prove
So
it.
wait, so it wasn't an if and only if.
It is an if and only if. Because I'm assuming that the group of rational points is finite.
Okay.
I had the two statements. Of course, it's that conjecture. If you can prove it, I'd be delighted.
It's about the last part. I didn't understand what is L. Is it finite extension of F or just sub-extension in M?
Well, no, it's sure. L is the p-Hilbert class field of F. So its Galois group is isomorphic to the p-primary subgroup of the ideal class. It's the maximal unramified abelian p-extension of F. So by class field theory, it's a finite group. Yeah.
Other questions?
So you define the EF and the UF, and the EF goes into the UF. What is Galois of M over L exactly? Is it just UF mod EF or something? Or what's the relation?
No. It's UF mod EF bar. That's
Okay, right.
That's the point. Because you have to, to look at that quotient of the ideal class group, you have to take a closure of a certain group in the topology of the ideals, and that's why you get EF bar, not EF.
All right, well, let's thank our speaker again. And we'll reconvene in 8 minutes.